It's a pleasure to be here today. Thanks to Bryce and John. Thank you all for coming. How many of you know what a blockchain is? How many of you have heard the term, know something about it? Couple of hands. Anyone consider themselves a blockchain expert? Think they know it really well? Well, that's great, because you're all going to be by the end of this talk. Really, I'm not kidding. I know you guys are laughing. That's not funny. I do have one thing to ask, though. If any of you have looked at my slides ahead of time, please still laugh at my jokes. It's important for my self-esteem. So I'm the chief cryptographer at Ripple, and I was one of the original architects of the Ripple consensus ledger, which is a blockchain. I'm known as Joel Katz in a lot of online communities. The company I work for is Ripple, the global leader in distributed financial technology. We're working on allowing people to move money the way they move information today. The Internet of Value and distributed financial technology to allow banks and financial institutions to transact directly rather than going through the correspondent banking system. We have 135 team members, 2/3 engineers, a lot of experience in different fields, and main offices in San Francisco, offices in New York City, London, Sydney, and Luxembourg. We're developing blockchain software in C++, have been doing so since 2011. So we've got a vast array of customers and partners working with major banks to move money more efficiently. So blockchains, what are they? What are they good for? Blockchains record state, and they record history. History, past state. State is modified by transactions. A transaction commands some change in the state. And the important thing is that transactions are eventually agreed on. So if you transfer a token that represents some value, everybody will eventually agree that that value was transferred. Assets, the things that blockchains manage, funds, whatever they are controlled by identities, which are represented by public keys. And they prove their authority by digital signatures. So a transaction is signed with a digital signature that connects it to an identity. The integrity of the blockchain is protected by secure hashes. And what that means is we can communicate a secure hash, and then we can follow a hash chain to find the history of the blockchain. Well, boy, that sounds an awful lot like something you guys probably know a lot about, right? I mean, that's a database. Databases store information. They have transactions that change their state. Is a blockchain just a database? Well, not quite. Because a blockchain does something that databases don't do, and that's manage the double spending problem. So if you're going to have some kind of a payment system, some kind of an asset tracking system, and Alice has an asset, let's say $10, she has to be able to send it to Bob, or we don't have a useful asset transfer system. And she has to be able to send it to Charlie, or again, we don't have a useful asset transfer system. But if she can transfer the same asset to both Bob and Charlie, again, we don't have a useful asset transfer system. So somehow, if she sends her $10 to Charlie, that has to prevent her from sending the same $10 to Bob. Pretty basic stuff. So how do we usually solve this? Surely we've had this problem before, and certainly we have, and we solve it with a central authority. So if I write a check to someone, my bank is the central authority that says that check is good. They prevent double spending by reconciling against their ledger. So they have a record somewhere that shows how much money everybody has, and they say that check is good, that check is not good. You could also imagine doing it with secure hardware. I could have some sort of box that knew how much money I had, signed a transaction to transfer funds, and then it knew I had less money. But someone has to put the keys in that box, and you wind up needing a central authority. It's very difficult to design secure hardware that we can trust without some central authority to put the information in that hardware. Before blockchains, we had a lot of effort to produce these decentralized asset transfer systems, Hashcash, which came up with the idea that you could use proof of work to create something scarce. Computers can only do so much work, however much work they can do. They can't do more than that. So you can create a scarce resource by attaching it to computing power. B-Money was the next step, which came up with the idea of essentially having some trust in the servers to solve the transfer problem. So Hashcash could regulate the control of an asset, but not a good way to transfer it. Somehow you had to know who held that asset. B-Money had the idea of trusting the servers. Ryan Fugger developed Ripple Classic, which had this idea of, instead of having one central authority, you would have lots and lots of authorities. So every asset could have its own authority, and that way no one authority ran the system, just an asset. The breakthrough came with Bitcoin, which was the first blockchain, and it is literally a chain of blocks. And by that I mean that each block has the secure hash of the block before it, so you can follow that chain from the current block through the history of the system. Transactions transfer a native token, so that as Bitcoin creates some sort of an asset, a unit, a transaction transfers that asset from one cryptographically proven identity to another. It has what we call a UTXO model. This gets a little technical, but it's kind of important to understand. A UTXO is an unspent transaction output. If you have a Bitcoin, you have a UTXO. A UTXO is essentially some Bitcoins that have been sent to someone, but not yet been spent. So a payment creates a UTXO. If I send you a Bitcoin, I create a UTXO that you have the private key to claim for that Bitcoin. And we assume the network agrees on the set of UTXOs. We don't actually directly check that, but if they agree on the transactions produce UTXOs, they should agree on the set of UTXOs. And the amazing thing is that Bitcoins meet all the requirements for currency. So they're scarce. You have to have something scarce in order for it to be a currency. If we can produce an unlimited quantity, well, I guess with dollars we can produce an unlimited quantity. But if there's something that regulates the quantity anyway, it's usable as a currency. So it has to be fungible. That means that the units look the same. So I don't particularly care what dollar bill you give me. It could be an old one. It can be a shiny one. But I treat it as a dollar. We don't use apples as currency because there are nice apples, there are not so nice apples. It has to be divisible. If you imagine we had only $100 bills, that wouldn't be a very useful currency. How would you buy cheap things with it? Bitcoins are divisible, and they're durable. So you don't want something that spoils. It's a terrible currency. You want something that's durable. And you want something that's easily transferred. So we don't use blocks of gold as currency typically directly because they're difficult to transfer. I would have to give you the block of gold. I would have to carry it around with me. So instead, we virtualize it into an asset that is transferable to fix that problem. So the amazing thing is that this native token on this blockchain meets all the requirements to be a currency, which means if people want to use it as a currency, they can. Bitcoin solves the double spend problem with mining. It also solves the distribution problem. If you imagine that you created a currency that had no central authority, how would you introduce it in the first place? There's nobody to give it away to people. There's nobody to sell it. There's nobody to give it away. So Bitcoin does it through mining, which is a computational contest. I used to joke that it's like giving them away to whoever wastes the most electricity. That's frighteningly close to the truth. The longest chain wins, so that is the chain that has the most computational effort wins, and miners are incentivized to lengthen the longest chain. So if you sent me a Bitcoin on the longest chain, that chain is going to get longer and longer and longer. The other chains are not because nobody's paying to lengthen them. And we have eventual consistency. As soon as the blockchain that has your Bitcoins on it is sufficiently longer than the others, you can trust that it's going to stay that way, and that solves the double spend problem in practice. It's also interesting to note that we have both a currency and a payment system. So we have Bitcoins in the sense that I can have a Bitcoin, and we also have Bitcoin, which is a blockchain that can transfer that asset. And you could imagine separating those things. That you could imagine a bank that issued Bitcoin certificates of deposit, held people's Bitcoins for people. It could have its own payment system. But Bitcoin is both a currency and a payment system because it's rooted in a blockchain that also supports transactions. And the system regulates the introduction of new currency. The way mining is controlled, it creates Bitcoins at a predictable rate, and the supply is ultimately fixed. So we actually have a deflationary currency. Some people love deflationary currencies, some people hate them, but that's what we have. The rules are notionally set in stone, by which I mean we all have software that controls what happens with a Bitcoin, and we can only change those rules by social consensus. So, for example, the Bitcoin supply is limited to 21 million Bitcoins by the software. But if everybody decided to change the software so it produced more Bitcoins, you don't have to change your software, but then you wouldn't agree with the rest of the world. And because the world does have to agree, it requires eventual consistency. Everybody has to agree on the rules and agreeing on changing them, which has been a bit of a governance problem. It has a UTXO model, and it uses mining to secure transactions. Ripple, one of the next blockchains. I have the worst elevator pitch ever for Ripple. It's a platform for issuing, holding, transferring, and trading arbitrary assets. I'll unpack that a bit. It began in 2011 when Jed McCaleb hired me to try to find another way to solve the double spend problem without a central authority. We came up with a distributed agreement protocol, which is kind of like a room full of people agreeing on something. As long as they all agree on which transactions to process and we can tell what they agreed on, that solves the double spending problem too. We replaced blocks with ledgers, and we allowed arbitrary assets. I'll go over that in a second. So we have ledgers. Ledger is the current state of the universe. It's just like the contents of a database. So instead of having unspent transaction outputs that are sort of collected over time, we have the ledger that has everything in it. And that forms a secure hash chain in Ripple. Transaction sets advance the ledger. An advantage of that is that prior ledgers can be forgotten. If anyone's ever tried to run Bitcoin, you know it takes a long time for you to synchronize the blockchain because you need every transaction that's ever happened. Prior transactions can be discarded in Ripple. You only keep them if you want history. So the ledger also contains the transactions themselves and what we call metadata. So metadata is what a transaction did. So if I pay you $10, the transaction, presumably, if it succeeded, paid you $10. For simple transactions, it's enough to know the transaction succeeded. If I write a check to someone, it's enough for everyone to know that that check went through. But imagine if you had a more complicated transaction. Say you had a transaction that paid someone 10 euros at the current rate, and you were willing to pay up to $12 to do it. Well, just knowing that that transaction succeeded isn't enough, because it doesn't tell you how much you paid. It doesn't tell you who provided the euros and who took your dollars. So a more sophisticated system that tracks what a transaction did can support more sophisticated transactions. It develops eventual consistency by an algorithm we call consensus, which is a distributed agreement algorithm. Any of you know what PBFT is? Good, you'll find out soon enough. It doesn't require 100% agreement on the participants. That was what was interesting about Ripple. Prior algorithms required everybody to agree on the participants. Ripple just requires substantial agreement, which means that you can add and remove people without having to agree on who's in and who's out. So it's Ripple's method of solving the double spend problem. Transactions are applied as a unit in groups. It's like a room full of people trying to agree. One of the reasons it's robust is that an honest server just cares about agreement. So if you imagine we were all trying to agree what to have for lunch, we all have different things that we want. Some of us don't like gluten. Some of us are on a low-carb diet. Some of us are vegetarians. It's hard for us to agree because we all have different interests. But imagine if all we cared about was agreeing. All everybody cared about is that we pick a place to eat. So someone says, let's go to the movie theater, and everybody's like, no, that's not a place to eat. And someone says, let's go to Burger King, and everybody's like, that's a place to eat. It's a much simpler problem when the different participants have aligned interests and they don't have unique interests. So if they all agree on just getting the valid transactions in, agreement is much simpler. The other interesting thing to notice is that you can solve the double spend problem just by putting transactions in order. Why? Because whether a transaction is valid or not is deterministic. If you want to spend money, you have to have it. Executing a transaction, if it transfers money you have, it succeeds. If it transfers money you don't have, it doesn't succeed. It's deterministic. We can all agree on it. And transactions either conflict or they don't. If I try to send the same money to two different places, we'll all agree that the second transaction will fail. But which is the second transaction? You might see one payment first and then the other one. Someone might see them in the other order. So transaction ordering is sufficient to solve the double spend problem. And that's what validators do in Ripple. They propose sets of transactions. They avalanche to consensus. Avalanche, if you imagine a snowball on the top of a roof. If it starts to tip in one direction, everybody kind of pushes it in that same direction, and so you reach agreement very quickly, and then they sign the ledger. So it turns out that this is remarkably robust for a set of reasons that make it seem a much simpler problem than it originally seemed. So one is all honest participants will vote to include a transaction if there's no reason not to include it. If I say I want to transfer $10 to Bob and I have $10, Bob's a valid account on the system and everything looks fine, every honest participant will say, yeah, that's fine, that should go in. And if a transaction has any reason not to be included, maybe it's part of a double spend, whatever, it's fine if it's not included, because if it's still valid, it'll be voted in the next round. And the algorithm is biased to exclude transactions to reduce overlap. So what that means is that if we can't agree, if there's a whole bunch of transactions and there's just lots of disagreement, we can reduce the amount of disagreement by eliminating transactions and not adding new ones. And that way the amount of disagreement continuously drops. It has no rotating dictators. So in Bitcoin, a miner chooses the transactions that go in a block. Consensus doesn't have rotating dictators, so you can do things like financial transactions, where if one person controlled all of the transactions, they might abuse that to their own financial benefit. They might take the juiciest offers, they might prevent people from moving funds, and so on. And the past can't be rewritten. Ripple is an open source ISC license, public ledger, public transactions, public history, equal access, and it's written in C++ by a team of developers who've been writing high quality modern C++ software for several years now. So how do you move assets on a payment system that isn't connected to any sort of financial institution? You might imagine if you have a payment system like Visa or eBay, they have infrastructure that moves real money. And you might wonder, how could you have a payment system that wasn't directly connected to infrastructure that moves real money? And the way you do that is by virtualizing arbitrary assets. So an asset is identified by an issuer and a currency, let's say dollars issued by Wells Fargo. That seems like a nice asset. And because an asset can be issued by anyone, Ripple only allows you to hold an asset that you choose to hold. So I don't want my cousin Jeff to owe me money. That's not a very reliable currency. I'd rather have Wells Fargo owe me money. I can choose. Assets have a counterparty, and what's interesting about that is that means they can reflect a legal obligation. So if RCL says that Wells Fargo owes me $10, while the ledger is reporting that and Ripple knows that that's true, there is a separate legal obligation on the part of Wells Fargo to owe me those $10. And presumably, even if something terrible happened to Ripple, that legal obligation would still exist. And you'll see in a minute what that does. So you have a bunch of accounts, their identities in the network, and they trust each other, forming a directed graph. So this shows that Alice is willing to allow Carol to owe her some money. Alice is willing to allow Edward to owe her some money. Of course, these would probably be financial institutions, but they could be people. And so you can have money by sending money in the physical world. So Alice can actually send $100 to Bob, and Bob takes that $100 and pushes an electronic asset to Alice. Now, that electronic asset can be in any system we want. It doesn't matter. What's important is that Bob owes Alice $100, and that's a real fact. The system is recording that fact, but it isn't that fact. That fact is a fact. Alice sent Bob $100. Bob owes Alice $100. So Alice now has this digital asset that says, Bob owes me $100. Alice can transfer that asset in any system we want as long as Bob is willing to honor it. So if Charlie also trusts Bob and Alice sends those $100 to Charlie in any system at all that Bob is willing to honor, it doesn't matter who runs it or owns it as long as it doesn't mess up, now Charlie can redeem those $100 with Bob. The only problem is if you imagine that we all have different people we trust and you get this sort of spaghetti network where there's a large number of participants and it's not a very usable system. So the solution is to have a hub. A hub would be like a bank. If there are a lot of people who are willing to consider Wells Fargo owing them $1 to be worth $1, then you'll consider it worth $1 because you know that other people will consider it worth $1. But now you wind up with a whole bunch of islands. You wind up with Wells Fargo issuing dollars. You wind up with another company issuing euros or issuing bitcoins or yuan or all these different currencies. So how do you make a global payment system out of an arbitrary asset system? With offers. Those things in the middle that look like those double arrows, those are connectors. They have an asset or an account in two different systems, and they're willing to trade one asset for another. So if I hold dollars at Wells Fargo and I'm willing to transfer them for euros, then someone who wants to make a payment can give me the euros I want, and I transfer the dollars at Wells Fargo. And you can put together an international payment from two domestic payments. So if I want to pay someone in China, and there's someone in China who's willing to accept my dollars in the US and supply the money in China, those two domestic payments, from my point of view, act like one international payment. So arbitrary assets, how do they work? Money doesn't really move. You notice we never actually moved any money. What we did is we changed who owned the money, and that's just as good. If Alice wants to pay Bob $10, what she wants is Bob to have title to $10, so he considers her to have paid him. So you don't actually have to move any money. You just have to swap the ownership of the assets. Sender loses custody of the asset they sent. The recipient gains custody. Payments ripple through the intermediaries. They gain and lose assets to facilitate the payments. They also benefit. Now, a crazy idea, you can build social credit out of that. So typically, if you need money, you borrow it from someone, typically a financial institution. I don't know how many people here borrow money from their friends, but that's not really socially acceptable. But what you could do is instead of borrowing money, if I borrow $10 from someone, they don't have $10. And they're out $10, and they might charge me interest, which makes sense because they take a disadvantage. But suppose instead of me borrowing $10 from them, we exchange IOUs. So I give them an IOU that says I owe you $10, and they give me an IOU that says I owe them $10. Those IOUs have value. Those IOUs are something that people will want if I have assets that people want. And you can build a system like this. Someone has money at a gateway. They have a whole bunch of people who trust them. They can push balances to those people. Now, here's where things get interesting. So Alice notionally has a $40 balance because the gateway owes her $100, but she owes $20 to each of 3 other people. But the gateway doesn't know that she has those IOUs. She still has that $100. Now, you might think that she can't spend that money, that she has to have a positive balance, that you wouldn't want to go negative. But if you think about it, every asset one party has is an obligation some other party has. The system funds have to sum to zero. If Alice has $100 at the gateway, it's because the gateway owes her $100 and has a negative balance. So a social credit system would allow everybody who wanted to run negative or positive balances and create value out of borrowing. works on Ripple today, but it's considered a pretty crazy idea. Government money is not about to go away. There's a lot of people who think that these things will take over the world. There's a multi-trillion-dollar market in these legacy fiat currencies, if you will. They're not going away anytime soon, so they are important. You may have heard of private blockchains. These are blockchains that are not accessible to the public. They're becoming very popular now for things like trade financing, settling securities, and other applications. They're like public blockchains, except the participants are controlled. So you typically have a cryptographic identity to use the system at all. Transactions can be private, and they don't need a native token. They don't have to worry about denial of service attacks because you can cut off participants you don't like. Attacks can be mitigated because you know the identity of the participants. They can react to a legal process. So there's no court you can go to get your Bitcoins back if they're stolen. There's no legal process that you can apply to the Bitcoin network because it's running on thousands of people's computers. And there's no real management. If any of you are familiar with the block size controversy, there's no way to manage a public blockchain really except to get agreement. A private blockchain can have a formal management process, and it can be built into the software. So they're good for organizations of frenemies. Now, if you imagine banks have a cumulative interest in making asset transfer reliable, but they don't want any one bank to run it. Wells Fargo doesn't want to use Chase's payment system. Chase doesn't want to use HSBC's payment system because they're business competitors. You can use a private blockchain to have a system where the rules are enforced by software. And because the rules are enforced by software, you have redundancy. If one system doesn't follow the rules, it just gets ignored by the other, and they can be self-governing. So that seems to be a way to save money. Traditionally, if banks wanted to set a payment system up between them, they would create an organization like SWIFT. It would have governance, it would have computers, it would have offices, it would be very expensive. They could solve those same types of problems using a private blockchain where software enforces those rules. No one person can cheat the system or control the system because the system works by agreement of the remaining system, of the participants. So a lot of Bitcoin enthusiasts seem to think that there'll be one ledger to rule them all. We've beaten down that path for a couple of years, and the news is there is not going to be one ledger. There is not going to be one payment system. There is not going to be one blockchain. There's not going to be, just like there isn't one web server, just like there isn't one payment system on the internet, there's one internet, but there's a whole bunch of different systems on it. And the reason for that is that people like different things out of their ledgers. And we want innovation. Ledgers are important. They track assets. People want high-frequency trading. They want ledgers that respond to government subpoenas. They want ledgers that have different rules. Some people want ledgers that are fully public. Some people want ledgers that are private. Some people will refuse to participate in a system if North Korea has access to it because they have regulatory requirements. There is not going to be one payment system. But we don't want ledgers to be islands either. We need a standard. We need a way to make payments across ledgers. We need a way to build a system that consists of a number of payment systems forming one network. Just like the internet connected a large number of private networks together, and we need a neutral standard. Ripple has proposed Interledger as a solution to connect payment systems to each other and build a world where money can move as easy as information. It's surprisingly simple. So you have ledgers that track accounts and balances, but you have people who are on different ledgers. A sender has a sender's ledger, recipient on a different ledger. These could be financial institutions, they could be payment systems, it could be PayPal, it can be anything. So we have a connector that relays money. Connector has an account in both systems and is willing to accept a payment on one system and make a payment on another. So if Alice wants to pay Bob, let's say Alice wants to send 100 widgets and deliver those widgets to Chloe. Chloe receives a payment on Alice's ledger, Chloe makes a payment on Bob's ledger, and everything is good. Except someone has to make that payment first. If Alice makes the payment first, she has to trust Chloe. If Chloe makes the payment first, she has to trust Alice. There are tremendous advantages to being able to use connectors we don't trust because connectors can compete. So money would be lost if Chloe drops the payment. We can use escrow to fix that problem. And the ledgers provide the escrow. I'll show you why that's important in a minute. So if Alice wants to send some money to Bob through Chloe, she puts the money that she's going to send in escrow. Then Chloe puts the money that she's going to send in escrow. And then the transfer is executed from right to left. So the recipient gets the payment from Chloe, Chloe gets the payment from Alice, and we have an atomic transaction. The recipient's receipt releases the funds to the recipient, but also the recipient's receipt also releases the funds to the market maker, to the connector, to Chloe. So Chloe receives the funds from Alice, Bob receives the funds from Chloe, and the transaction is atomic. So transfers are executed from left to right. They're escrowed from left to right, executed from right to left. The ledger only has to support two operations. You have to be able to put the funds in escrow. That is, you have to lock them up so that everybody knows they're going to be there, and you have to be able to release them. And as it happens, just about every ledger in the world can already do this. Every banking ledger has a way to hold funds while they're in transfer, has a way to clear the transfer. So you can make transactions across ledgers facilitated by connectors atomic just by adding two operations to each ledger, operations that they can easily support. Interledger has a set of crypto conditions, which is a standard that specifies how to agree on whether or not something happens so that we know that Bob's receipt will release the funds from the sending ledger. The key is one ledger's receipt is another ledger's receipt condition. So it's the receipt of the funds to Bob that triggers the release of the funds to Chloe. Leverages the trust that already exists. Anyone who has funds on a ledger trusts that ledger. Anyone willing to receive funds on a ledger trusts that ledger. And you don't have to trust the connectors. So if you look at it from Bob's point of view, let's say Alice is sending Bob money, which is either going to create a legal obligation for Bob. Maybe Bob's going to send her some goods. Or maybe Alice already owes Bob money. Bob doesn't want to give the receipt and not get the money. And he doesn't trust Alice or Chloe. Alice wants to send the money. She doesn't want to lose the money unless Bob gets it. She has to trust her ledger since it has her money. Chloe, the connector, doesn't want to pay Bob and not get paid by Alice. Chloe has to trust both ledgers already because Bob's ledger has her money and Alice's ledger will have her money. She doesn't trust Alice or Bob. She doesn't want to pay Bob unless she gets paid by Alice. And all of those requirements are met. All of those requirements are met by this system because Alice cannot lose her funds without the receipt that Bob got paid, and Chloe knows that when she gives that receipt to Alice's ledger, she'll get paid. Boy, it seems so simple. I think some of you probably know it's really not that simple, unfortunately. So sometimes it is that simple. Sometimes it is that simple. So why? Well, when the sender puts funds into escrow, Alice locks up her $100 for this payment. And the release condition, Chloe gets that money when Chloe pays Bob. Seems good. The problem is we need a failure condition. We need some way to unwind this if it doesn't work. Why wouldn't it work? Maybe the connector can't meet the payment terms. Maybe the connector loses connectivity with the internet, a ledger breaks, something can go wrong. We need some way to unwind this transaction if something goes wrong. Now the sender, from Alice's point of view, she doesn't trust the connector. She doesn't want the transaction in limbo for an hour because if Chloe doesn't make the payment, she's lost an hour of time, the connector's held her money. But if the sender has to meet a release time that's tight, the connector is taking risk. The risk stems from the inability to get the receipt to the ledger. So the problem for Chloe is, what if Chloe pays Bob and then something goes wrong? Chloe can't get the money from Alice, the time expires and Alice gets her money back and the connector's out. So for low value payments, it's not a problem. You can use a release time, say 10 minutes, and Chloe can price in the risk of failure. So if there's a 1/10 of 1% chance of failure, she can charge 2/10 of 1%. Not a problem for small payments. Not good for high-value payments. For high-value payments, you need to agree on whether a transaction succeeded or failed. You can't have this situation where one ledger thinks the transaction succeeded and another ledger thinks it's failed. And you can't have a long lock time. If I want to make $1 million payment to someone, I don't want someone having the option to make that payment for an hour without being committed to make it, because maybe they'll wait until the financial markets move for their benefit and they'll make the payment if and only if they get an unusual fee. So you need proof that something didn't happen. If the payment doesn't happen, you need proof, and simple schemes cannot provide this proof of absence. Fortunately, we do have a scheme that can provide proof of absence. It's a fairly new technology, and it is definitely being underused. It comes from the Byzantine generals problem. How many people here are familiar with the Byzantine generals problem? Anyone know the Byzantine generals problem? I'd say probably 10, 15%. So the basic idea is you have two generals, they have two armies, and one of them realizes that if they both attack a city the next day, they'll be able to take it. But if they attack alone, either one of them alone will not be able to take the city. So the general that realizes the plan is going to send a messenger to the other general saying, let's both attack the city tomorrow. The problem is the messenger might not get through. But that's okay. The receiving general can send a messenger back saying, hey, I got your message, I'm attacking tomorrow. But what if that messenger doesn't go through? Does the sender attack or not? And the problem is you can prove fairly simply that there is no solution to this problem, as stated, even with very simple requirements. So simple requirements would be, if no messages go through, you can't attack because you don't have a joint plan. If all the messages go through, then both have to attack. Otherwise, you don't have a solution, even if nothing goes wrong. And then the other requirement would be the number of messages has to be finite. If you have a message that requires a protocol that requires an infinite number of messages before it reaches a conclusion, that's not a useful protocol. Now, it seems that those requirements are simple and reasonable, but they're too many. There's a very simple formal proof that there are too many. I'll give you the formal proof just in case anyone can follow it verbally, because it's cool. And then I'll give you an informal proof that's easier to follow. The formal proof is this. If there was some algorithm that guaranteed that both generals attacked or neither general attack, it has to have a finite number of steps. Let's call that n. So we have this algorithm that sends n messengers, and then if no messengers fail, they both attack. Now imagine if the last message doesn't go through, and no messages after that go through. Well, the person who sent that message doesn't know that message didn't go through, so they still attack. And since the algorithm presumably guarantees that either neither of them attack or both attack, that means they both attack. Well, if they're both going to attack, even if the last message doesn't go through, what's the point in sending the last message? Just don't send the last message and the algorithm still works. But we have a problem. We said that this was the message with the shortest number. This was the protocol with the shortest number of messages, and we just found a protocol with one fewer message. So we have a contradiction. If we have an algorithm that works with n messages, we have an algorithm that works with n minus 1 messages, which means we don't have any algorithm at all. A more informal proof is each general is only going to commit if the other side commits. At some point, some general has to commit irrevocably. Some general has to say, even if no more messages go through, I'm attacking. If nobody ever commits, it never finishes. And someone has to commit irrevocably first. Some general has to be the first general to say, okay, I've gotten enough messages, I've sent enough messages, I'm attacking. But we can't commit irrevocably until we know the other side has committed irrevocably, so neither side can commit irrevocably first. It's a little more informal, but a little easier to follow. And it also helps you to identify Byzantine generals' problems. When that argument applies, you have a Byzantine generals problem. Many of you probably know that the TCP protocol does not guarantee that either both sides will see an error or neither side will. How many of you know that? Most of you know that? Doesn't provide that guarantee, and it can't provide that guarantee because that's a Byzantine generals problem. So we have this sort of, you send these sort of, I'm done, I'm done, I'm done. I hope you got one of those messages. Maybe you didn't, but I'm not going to transmit anymore. But we do not guarantee that neither side will see an error or both sides will. It also creates an interesting problem. Like you might think it's a simple problem to say I'm sending an email from one server to another, and I want the sender to stop sending the email if and only if the receiving machine got it. Again, Byzantine generals problem. We run into the same complication. But we have an algorithm that solves the Byzantine generals problem. I know I just said there was no solution. It solves the problem by changing the constraints a little bit, but it's a realistic, practical solution. In fact, the PB in PBFT does stand for practical, I hope. Anyone know for sure? Am I misremembering? I think it stands for practical. If not, it could just as well. So it's a Byzantine agreement protocol, and it can tolerate some faulty nodes. It can tolerate drop messages so long as enough of the nodes don't fail. And it combines beautifully with crypto. So as PBFT was originally specified, it didn't use any cryptography at all. It combines nicely with crypto. So what you can do with crypto is, since all the participants are known, you can give them a cryptographic identity, and so they can't impersonate each other. They can't send one thing to one participant, another thing to another. That makes PBFT run really nicely. Another advantage is if you know what threshold signatures are. Threshold signatures are cases where you get cryptographic signatures from, say, 7 out of 10 participants or 8 out of 13 participants, and you can combine them into a single signature. So what you can do is, if you have a Byzantine agreement protocol and you have the correct quorum agreeing, let's say 8 out of 13 agree, you can produce a single digital signature as a proof of that agreement, which is really, really nice. High-value payments in ILP is a BG problem. So we want the payment to Bob to happen if and only if the payment to Alice happens. And what that means is that the two ledgers need to either agree that the payment happened or agree that it didn't. Consensus in Ripple is a BG problem. We want all the servers to agree on the transaction ordering. We don't want someone to pick a particular ordering unless everybody else does. The double spend problem, the distributed ledger, the distributed database agreement problem, these are all BG problems. In fact, lots of problems are BG problems, and we now have a solution to the Byzantine generals problem. Essentially, we gather an army of witnesses, and we let the witnesses come to a consensus on whether we're going to do it or not. They provide a digital signature, and then everybody knows from that digital signature. The thing that we give up potentially is liveness. If the system fails, then nobody may know what happened until the system recovers. But that only happens if a quorum fails. And we can minimize the probability that there's not a single point of failure. We can control the number of points of failure. So it's easy to solve with algorithms like PBFT, and we only need those agreements to be private and ephemeral. You can also do that with private blockchains. Private blockchains use Byzantine agreement protocols like PBFT. So if you imagine a consortium of banks that set up some payment system, they can set it up so that if 8 of the 13 banks agree on a transaction, the transaction goes through. They can use something like PBFT to agree on that transaction. Okay, now we're all blockchain experts. There is going to be some development in C++ content, I promise. Promise, we're getting there. But I had to make you all blockchain experts first. Those are blockchains, that's what they do. So why are they hard to develop? What's so difficult? What are the unique software challenges that we need to solve with C++? First of all, they have to be fortresses. How many of you are familiar with any Bitcoin thefts? There was a $70 million theft just recently. You probably know. It's a huge, huge, huge problem. And the reason the problem is so big is a couple of things, but one of them is that we don't have a financial system built into the ledgers that can track the funds and recover them easily. Once the Bitcoins are transferred, they belong to another cryptographic identity. They can sit silently for months or years, and there's no way to recover them. There's no legal process. Well, I guess you could have a hard fork. Any of you know about the Ethereum hard fork? You can sort of have everyone agree to wind the ledger back, but that didn't happen for a $70 million theft. And the code is public, so you can't hide your flaws. You can't put in a comment, if anyone figured this out, we'd be screwed. You might not put the comment in, but someone will figure it out. So this is the problem. You got a multi-billion-dollar bug bounty. So there's a tremendous incentive for people to find the bugs. And because if they find bugs, they could steal potentially millions of dollars, and they're very unlikely to get caught, that stresses people's morals a little bit. I know if I found a bug in Cisco software, or if I found a bug in, Apache, I would probably do the right thing and tell the community. But if I found a bug that I could make $70 million on, and my probability of getting caught is pretty low, I like to think that, I would do the right thing, but I won't ask for a show of hands who would do the right thing in that circumstance, because I don't think you'll be honest. But, it's a huge, huge problem. I can't stress how big a problem it is. And the other problem is, even if it doesn't allow a theft, let's just say it corrupts the blockchain. Let's just say it creates an invalid state on the blockchain. You have to get everybody to agree to rewind it, and that's not an easy thing. We've had very good luck. Bitcoin had a problem like that. There was a hard fork between two. It was an inadvertent mistake. A small bug in the software caused the two versions of the software to have different rules for what makes a block valid, and so they didn't agree on what the longest chain was. And there were double spends. There were spends on one chain that weren't on the other chain, and people lost money. It's impressive that the community was able to come together and agree on how to fix that, but that is very, very painful. Very painful. This makes development slow. If you're developing software that everybody can see the code to, development is much slower. I guess an analogy would be, imagine you're building an operating system like, let's say, Linux, and you want to protect it from network attacks. That's not too bad. Now you want to protect it from local attacks by people who have user accounts. That's a lot harder because people have a lot more access to the system. They have a lot more knowledge. They have a lot more control. It's much more difficult to protect the system against a local user than a remote. Maybe makes development as much as 10 times slower. Maybe not quite that bad, maybe worse, depending. Very, very paranoid. The other problem is when you're developing mission-critical software, typically you put out a new release and you tell people, if your software is mission-critical, don't upgrade to this release. Just wait. Unless there's something you really need, just wait. Test it out, see how you like it. Blockchains have to have agreement by the entire world, so we can't do that. We can't tell people that they can run a new version of the software unless they run it on a separate network. And one of the problems is, if any of you have released betas and you try to get bug reports, you always get the bug reports 5 minutes after the beta goes gold. That's always what happens. People won't test a beta. You try to get them. Hopefully big businesses, if it means a lot of money, they will, but they won't because they have to build duplicates of their systems that work on the beta. It won't replicate the real situation because they're not going to build everything on the test system. So public blockchains must be fortresses, and that is one of the reasons that we like C++, and I'll show you why later. We also have to manage our resources. We have to keep up with the network. We don't want to fall behind. People want to know that they got their money immediately. If someone's making a payment to us, instant satisfaction is extremely important. One of the big advantages of these systems is that they're quick, so we have to keep up with the network. We can't just fall further and further behind. Some servers have to respond to remote queries, so remote servers will ask them for information. They have to manage those resources and not fall behind. Some of them have to deal with local queries. So the Bitcoin network stays stable because people are willing to give information to each other. If I need history, if I shut my server off and turn it back on, other servers generously give me the information that I missed. They have to be able to do that without overloading themselves. And because it's a public network and there are no identities, they have to protect themselves against attacks. They have to manage their resources intelligently. They have to cache. You have no choice. You need binary formats for data representation because you have to sign transactions. All kinds of objects have to be hashed. That requires a single binary representation. You have to have unique binary representations. But humans don't like binary representations very well. That's why I'm not giving this talk in ones and zeros. JavaScript likes them too. JavaScript likes JSON a lot. And if you're not careful, you can wind up with a situation where if you push something to JSON and then back to binary, you don't get exactly the same binary data back. And you need that because otherwise the signatures and hashes won't check. So you need good binary formats. And you need performance on everything. So some tasks are embarrassingly parallel. A good example is checking digital signatures. One of the biggest things that blockchain software does, it's a significant fraction of its computational effort, is it checks the digital signatures on transactions. Because these use public-private keys, they don't use shared keys because no one's going to share their key that controls their money with anyone else. That's a lot of work, checking those digital signatures. But it parallelizes beautifully. Once you have the key, the transaction, and the signature, you can check whether the signature is valid once and for all. You don't need any other data. It's self-contained. So that parallelizes beautifully. But some tasks don't parallelize at all. So when you're executing the transactions for real, you have to execute them one at a time because you can't have two transactions that conflict with each other. And it is all important. You need super high performance, both for the things that parallelize and the things that don't. Some languages are really good at one. Some languages are really good at the other. There aren't that many that give you a lot of flexibility to do both. And blockchains do not scale horizontally. We can't make Bitcoin handle more transactions by adding more servers. It doesn't work that way. Every server has to see every transaction to know the state of the network. And so we're limited by essentially the slowest machine we're willing to support. We do not have horizontal scaling of blockchain yet, so performance is super, super important. Naive C++ code compared to naive JavaScript code, let's say, to solve the same problem is about a factor of 5 in performance. So you really need to be able to control what you're making the system do. We also need isolation because transactions have to be deterministic. Some designs fail catastrophically. If you imagine that I send out the same transaction to two different machines and due to some software bug it produces different results on those two machines, then we won't have eventual agreement, we'll have disagreement. And that would be very catastrophic. It's very easy to get non-deterministic behavior by accident. You'd be surprised how easy it is to accidentally write code that behaves in some kind of non-deterministic way. Unfortunately, it is fairly easy to do, especially in smart contracts. Smart contracts is essentially code that manages intelligently the movement of assets. It's very easy to accidentally make a smart contract that's behavior is non-deterministic. And if the system crashes or fails or something horrible happens when you have non-deterministic behavior, that's a problem. The way you solve that is isolation. You don't give the code access to anything that's non-deterministic, so it cannot behave non-deterministically. So finally, the C++ content. So how do you meet these challenges with C++? Well, that's what we've been doing. We've been writing blockchain software for many years in C++. The Bitcoin project's primary implementation is in C++. C++ seems to be probably the primary language of choice here. So what does C++ do? And a lot of this stuff, almost everything except one thing is specific to C++. It's not in C. So if some of you guys are trying to persuade people to switch from C to C++, that they need to get with the times. Some of these points may help because these are things that are, except for one of them, these are things that are difficult to get in C. So one of them is move semantics. Move semantics allow types to have value semantics. So by value semantics, I mean a type that behaves like an integer. You can pass it by reference. You can pass it by const reference. You can pass it by value. You can stash it in a lambda. You can store it in a container. You can do whatever you want with it, and you don't have to worry about some weird requirement that's imposed on it where it doesn't really behave like a value. So move semantics mean that you only get copies when you need them. And one of the big problems with value semantics is that you get copies everywhere. You just wind up with code that has lots and lots and lots of copies. Move semantics eliminate a significant fraction of those copies with minimal effort, sometimes none. Usually very, very little effort. Huge, huge performance boost. C++ has lambdas, which enable visitor patterns and allow you to preserve layering. So what I mean by that is imagine you have a container and you want to perform some operation on that container, but it's complicated. So you need to acquire a lock on the container, perform the operation, and then release the lock. Well, you don't want the container to export its lock. That's a layering problem. We want the container to manage its own locking. So with a Lambda, we can package up the logic that's going to apply on the container and hand the logic to the container. The container can acquire the lock, process the logic, and release the lock. And that allows the lock to be managed by the container. Lambdas also allow work to be deferred and dispatched, so we can package up some work that has to go into a Lambda. If that work needs to be done later, we can pick it up when we're ready. I don't know if many of you are familiar with Boost coroutines, and I understand the standard library. There's some work on coroutines for C++17. Tremendously valuable to be able to do some work and then defer it until you have some other information that you need and then resume the work. Very, very clean and elegant. You don't wind up having to package all the information into an object or doing other ugly things with your state. Big one for us is compile time polymorphism. This has been massive, mostly because polymorphic code fully optimizes. So if you use runtime polymorphism with virtual functions, it's very difficult for the optimizer to optimize through because the compile time, it has no idea what function is going to be called. Compile time polymorphism even inlines, and it allows you to separate responsibilities cleanly. So you can put some of the code in the polymorphic class, and you can put some of the code in the code that calls it. The responsibilities separate nicely, and you still get optimization all the way across it. Tremendously valuable. C++ has type composition, which means you write code once and you get a nice API. Boost optional is a good example. Going to have standard optional, we'll see. Standard shared pointer and weak pointer, same thing. So I can take any class and I can wrap it in Boost optional or shared pointer or weak pointer, and I know what I'm getting. I know I'm getting an optional class, so I'm getting a class that has strong and weak pointers. I get a very nice API, and I don't have to tweak it for the class or do anything fancy, and it all optimizes through. We have code isolation features. We have namespaces. We can import one namespace into another, which we don't have name conflicts, helps with large-scale development. And the other thing that has also proven to be very valuable is that a class can be a boundary between two APIs. So a class can have an API for its use, those would be the public functions, and it can have an API for derivation, those would be its protected functions. So a class can be an API boundary providing two clean APIs, one on each side. Those can be documented, maintained, have different implementations, different clients. Extremely useful. We have a lot of mature tools. We have at least 3 solid compilers. We have ICC, we have GCC, we have Clang. We have tools for performance analysis. We have tools for finding concurrency violations. You name it, we have nice graphical IDEs. We have libraries for just about everything. It's not a new language. It's extremely mature. The tool chain is mature. Except sometimes I think we've all had this experience where you have an extra pound sign or an extra semicolon in a header file. This was a 32K error message. None of this code is the code that had the error in it. This is just a randomly selected excerpt. There's some Boost code in here. I don't know why. If any of you guys can do anything about that, that is a minor irritation and source of amusement. But I guess a source of amusement is a good thing. We all get bored sometimes. This is also a C feature. This is the one C++ feature that's not just C++. We have hand-optimized primitives. So very little code is worth hand optimizing. You're not going to write a major project in assembly language. You'd have to update it for new CPUs. And no. But there is some code that benefits tremendously from hand optimization. Digital signatures are a good example. Digital signatures are worth hand optimizing. And one of the amazing things about both C and C++ is these calls are really cheap. They can even inline. So you can have a piece of hand-optimized assembler that will inline into your C++ code, and the optimizer will optimize across the inlined assembly code. That's pretty amazing. That's pretty amazing stuff. Like in other languages, typically you have a function that can be hand-optimized, but then when you call into the function, you might have to push stuff on the stack. When you return from the function, you have to pop stuff off the stack. And it becomes like a hard optimization boundary. Everything in the registers gets pushed to memory. You don't have that in C and C++. And we can leverage work across projects. So if someone makes a digital signature implementation, we can use it in any number of projects. We have lots of mature libraries. I did have to include one bad thing, which is the slicing problem. I think that's probably the biggest problem in C++ right now, at least from the development that I've done. We like value semantics. We like classes that behave like integers, and polymorphism and value semantics mix badly. So if you have a reference to something or if you have a pointer to it, you can't easily copy it. You can't necessarily stash it somewhere. You can't manage its lifetime. That's a problem. We have a lot of solutions that sometimes aren't the right solution. You can take a raw pointer, and at least then you can pass it around. You can have a unique pointer. At least then the lifetime is managed for you. But what if you need to stash it in a collection? You can use a shared pointer. Pro tip. You can create a standard shared pointer to tconst, where the const is inside the parameter to the shared pointer. That way you're giving the callers a const It's not the shared pointer itself that's const, it's the t that's const, which means they can't change its value. One of the problems with shared pointers is if you pass them all around and someone modifies the object that the pointer points to, it modifies every instance of the object. You want to catch a mistake like that at compile time. Make a shared pointer to a t const, can't manipulate the object, you'll catch those errors at compile time. So the clone idiom, you can have a virtual function that duplicates a class. It's not a great solution. It doesn't wrap into standard containers nicely. We have boost pointer vector. But there are often situations where one of these solutions is the solution. Not a big deal. If you can use it, compile time polymorphism is the best solution for all the reasons that I discussed before. Compile time polymorphism because of the optimization. Catch bugs at compile time, it's really nice. Standard variant, if it gets into C++ 17, I think there were some talks about standard variant. Standard variant is a discriminated union, so it knows what type it is, and it can say, if I'm holding this type, we call this function. If I'm holding this other type, we call this other function. You can get polymorphic behavior in a type that knows how to copy itself without having to use a clone idiom. So, let me give you some very specific examples of, wait. That slide's not, sorry. There, much better, sorry about that. Let me give you some specific examples of things that we've done in C++, ways that we've built up software capital, ways that we've eliminated technical debt, ways that we've used modern C++ idioms to produce high-quality blockchain code. So one of them is in our caching. We use strong and weak pointers. The cache holds strong and weak pointers. And this is, oh look, someone's on Skype. I meant to put it in airplane mode and forgot. Any of you know who Pedro Moreno Sanchez is? He's available if anyone. Anyway, so we use strong and weak pointers in the cache. The cache will either hold a strong pointer to an object or a weak pointer. The strong pointer keeps the object alive, and the weak pointer doesn't. When you access an object, we promote the weak pointer to a strong pointer so that the cache keeps the object alive. Over time, rather than expiring the object from the cache, we throw away the strong pointer and keep the weak pointer. And what that means is that if an object is in use, if someone has a strong pointer to it, they pin it in the cache. And this has had tremendous benefits. Like I said in the slide, good things happen for free. So for example, suppose you have a ledger or some object that you're manipulating a lot. If you just share a strong pointer to it, you've pinned it in the cache, and all your other code can find it. So if you have objects that are valuable that you need to have around, you have some class that has a strong pointer to them, you're also making those objects available to all of your other code. So frequently used objects get pinned in the cache by use. Worked out very well for us. It also resists algorithmic complexity attacks. An algorithmic complexity attack is when an attacker who knows your algorithm carefully crafts his data to make your algorithm give its worst case performance. So if you imagine a sorting algorithm that maybe it has its worst case behavior if the data is already sorted, and an attacker can give you data that's already sorted, you get the worst case behavior. You can't keep your code secret, so you have to protect yourself against an attacker who carefully crafts his data to make your code behave in its worst case. And the way we do it is we index with salted hashes. So a salted hash, we hash it. We use a random salt. The attacker doesn't know the salt, and so he cannot attack the hashing algorithm. NewDB is, all of our code is open source. All of this is widely available. We've been promoting NewDB. It's something we built to solve a problem we have. It's a key value store. Stores fixed length keys and variable length data. And you retrieve only by key. We typically use it in a blockchain with the key being the hash of the data so that you can follow hash chains very efficiently. We have transactions, we have hash trees, we have ledger state entries, all kinds of things that we need to find by a key. So you probably know that there's a lot of key value stores out there. You've probably heard of things like LevelDB and RocksDB and all kinds of other things that are key value stores. The problem with all of them is that the memory demand scales with the data size, or the performance drops as the data size increases, or both. And that's because they rely on caching for performance. So for example, RocksDB is a phenomenal key value store, but you either have to use Bloom filters or you don't. If you use Bloom filters, the size of the Bloom filters is O of n. Double the data, you have twice as many Bloom filters, takes twice as much space in memory. If you don't use Bloom filters, then the performance is O of log n. So as your data gets larger, the performance drops. What we want is we wanted a key value store that's memory usage was O of 1 and whose performance would level off. So once you exceed a certain data set size where caching doesn't work anymore, rather than the performance continuing to drop or the memory usage increasing, the performance levels off, and it levels off at a very high level. So when we designed it, we assumed that caching was useless. We just said, let's assume that we can't cache. Our data is so large, our memory is so small, that we can't cache at all. We want our performance to level off as the data size increases. We don't want it to keep dropping. Unfortunately, we can't get it to keep increasing. That'd be awesome, but I don't know any way to do that. So the performance will level off. The performance will ultimately be O of 1. And therefore, there's no penalty for massive databases. And the memory use only scales with the write rate. We have to buffer the writes in memory to journal them. So if you have a very high write rate, you have some memory consumption. But the memory consumption is independent of the data set size. So we wondered, what was the best that you could do? If we could make the best possible key value store that had these requirements, how good could we get? What did we think was theoretically the absolute best we could do? And so we figured, if you're looking for data that's not present, maybe you could magically know where on disk the information that it wasn't present was. You couldn't have it in memory because we're assuming caching is useless. So you have to go to the disk. But the best we thought what you could do is 1 IO. You know where to look, you read that chunk, and it says, oh, the data's not in the database. So what about data present? What did we think is the best you could do? We thought 2 IOs. 1 IO to go check to see if the data's there, and that would tell you where the data was, and then you'd have to 1 more IO to get the data. So if data is not present, 1 IO. If data is present, 2 IOs. And the performance limit would be your SSD IOPS. So if you have an SSD that has 100,000 IOs per second, you could retrieve 50,000 objects per second, or you could determine that 100,000 objects per second were not present. NewDB is very, very close to that, like within a couple of percent. NewDB is very, very close to what we thought was the optimum that you could possibly do. The data is append only. We have a data file that holds all the data. It also holds the keys, so you can recover the index from the data in case it gets corrupt. It uses either 2 or 3 files. So you have the data file and an index file, and then during an update, writes are journaled. So you have 3 files only during an update. The index consists of hash buckets, and the bucket count is dynamically increased. So when we have more data and our buckets are starting to get full and we hit a configured limit, we add another bucket. We split a bucket in half to add another bucket, and we keep the average number of objects per bucket constant. Writes don't block reads don't block reads don't block writes, nothing blocks anything else. So ultimately, it is the SSD IOPS limit that is your limiting factor. So what does that have to do with C++? Well, it's header only, which gives you all of the advantages I talked about before about optimization. It uses a templated visitor and compile time asserts, which I'll show you. So this is the templated visitor. It passes the visitor function into the function that's called on each object into the visiting function. So that way you don't have to export an API that keeps track of where in the file you are. You just push the function that does the visiting in. It also templates on a codec. If you have any particular compression algorithms, if your data has any use case specific compression that's possible, for example, if it has a particular header, you can optimize that header out with a codec. We also use a static assert. Something very nice in C++ is that you can catch lots of errors at compile time if you're clever. This actually caught an error. Someone went to compile NewDB on a platform where the size of a size type wasn't big enough to hold the size of their hash. We assume that it is. This static assert caught that at compile time, which is very nice, saves you a lot of time. Beast, how many of you, whoops. So Beast, how many of you have gotten one of these from Vinny Falco? Anyone? No one? Vinny Falco would like every single one of you to have those. Beast is a library that we developed for HTTP and WebSockets. Vinny's been pushing to try to get it included into Boost, maybe. We'll see, maybe a little optimistic. It's header only, and it provides a Boost-like API, so it's an extension of Boost for HTTP and WebSockets that provides both asynchronous and synchronous APIs. You probably can't see this code, but take my word for it. It's really clean, elegant, simple code. It actually does something useful. One side on the left with WebSockets, on the right with HTTP. It's very, very Boost-like. Another example is polymorphic currency types in Ripple. If we had it to do over again, we probably would use standard variants for this. We didn't at the time. Ripple has both a native currency and arbitrary assets. Some objects can hold either type of currency. Some objects can only hold one kind of currency. We have a mix of code, some of which deals with multiple assets, some of which doesn't. Virtual functions were not a good fit. Slicing is one of the issue. Optimization is another. Another one is that you have all of these annoying runtime checks, like what if I got an object of the wrong type? And if you put a check for that into your code, you have to sort of do something if you have an object of the wrong type. And since it's one of those can't happen situations, you put in an assert, but then you can't test it. You can't unit test code that's never supposed to happen. It's very ugly and inelegant. It's a way to build up technical debt. Instead, you can use runtime polymorphism. It knows the type. don't have that problem. Templates give you concepts. I think most of you know what I mean by concept, but I mean essentially a set of rules that a class has to follow in order for a template to work. And they can't slice. And they keep the common code simple and easy to understand. So some of the code goes in the class that you're templating on, some of it goes in the template code itself, and it allows you to avoid having to have all of these, if it's this type of asset, do this, but if it's this type of asset, do this other thing, which gets to be very, very ugly and difficult to maintain. This is an example of one of the advantages of using that type of templating and compile time polymorphism. So this is a class that handles an offer of someone willing to trade one asset for another. And you can see it's templated on the type of assets. And what's nice about that is you see that boost optional T out at the bottom? You get value semantics. So that has value semantics. We can create a new object of type, whatever the output type is. We can wrap it in a boost optional. Very difficult to do that with virtual functions. Very difficult to do that with inheritance. But you can do that very cleanly with compile time polymorphism. Tremendously simplifies the code and makes it easier to maintain. That's it. Hopefully you all are now blockchain experts. Lots of time for questions if anyone wants to come to one of the two microphones.
Excuse me, you said that there was an attack on worst case behavior, but is there any sort of attack that can happen on the best case behavior? For example, let's say that your worst case behavior was n log n, but your best case behavior was linear time. Could somebody create an attack on that case where they're giving you the best data that can go through your algorithm and just get the best time?
Yes, but you would hope that that would be an easier problem to solve. Otherwise, you pick the wrong algorithm. So if someone attacks your best case behavior, all of your normal congestion control mechanisms would solve that. So for example, if you have a public blockchain like Ripple or Bitcoin, you pay a transaction fee. And those fees are normally very low, but if the network gets congested, the fee goes up. So if you want to keep the network congested, you have to keep sending transactions that saturate the network, and you have to pay a fee for every transaction that's greater than I'm willing to pay for my one legitimate transaction. So as long as you don't have an advantage over me, then I can compete on a level playing field because I only have to get 1 or 2 transactions free, and you have to keep the network saturated forever. Like if you want to stop me from performing a transaction, you have to keep the network saturated. If you're willing to pay more than me for a period of time, yes, you can lock me out. But what we really don't want, what we can't handle with the conventional methods, is someone who has a computational advantage. Like if you could submit one transaction and it cost 100 times as much as my transactions, now you can jam the network at a low cost, and I can't outcompete you. So we design the system to tolerate the best case behavior, and then we design it so that an attacker can't force the worst case behavior. Go ahead.
I have a question. We probably have soon quantum computers. Are your algorithms ready for that in Ripple?
For what computers? Sorry?
Quantum computers.
It's a good question. So we have to keep our eye open. We do have ways to evolve the algorithms, so we can swap out the algorithms if we get to that point. We keep a very close eye on that technology, as everybody who does encryption and digital signatures have to. I hope we still have about 8 more years before we really have to get aggressive about it. I could be wrong about that, but yeah, we do follow the technology as everybody has to. Everybody in cryptography, everybody who deals with electronic security. These systems are dependent on cryptography. They're dependent on secure hashes. They're dependent on digital signatures, and we have to make sure that the algorithms that they use are resistant against attackers who are willing to potentially spend millions of dollars to break the system. So yeah, we will have to evolve the algorithms, definitely. A lot of people will say, well, why don't you change the algorithms now? Like, why don't you, like, ahead of time? It's kind of like turning the steering wheel on your car when the curve's still 50 miles ahead. Like, you might do the wrong thing. It's hard to know, like, what a quantum computer is going to look like, what algorithms are they going to break and how badly, what are going to be the best algorithms to resist them. If we switch too early, we might find that we just have to switch again. So there's a matter of finding the right time, and I think we still have a couple of years. But yeah, we have to be ready. We absolutely do have to be ready. We have to follow the literature. And we also have to worry because we don't know what an attacker might have that is not in the literature. So I'm sure the NSA is a couple of years ahead of what we know about, and I'm sure foreign governments might potentially interfere with these systems as the amount of money they hold goes into the billions of dollars. So yeah, we have a huge bug bounty. We have a huge security bounty of potentially millions or billions of dollars. So yes, very concerned about that. On this side?
So for a ledger system with large number of participants, what is a typical quorum number? How many you have to get replies? How many systems you get replies from before you decide that it's an agreement and consensus and you can move forward?
So it depends on the type of system that you're using. In Bitcoin, it doesn't use a quorum, it uses proof of work. So it's just essentially sufficient hashing power by anyone. Ripple uses 80% of the active participants, but it identifies active participants essentially by known identities, so someone has to convince you to count them, because if you just counted anyone who was present, an attacker could produce thousands and thousands of identities. Private blockchains, typically, they know all the participants because they have some sort of an organization that said, like, these 10 organizations are the participants, and so they typically will use a quorum of 3n plus 1, where n is the number. So if there's 3n plus 1 participants, n of them can be missing, and you can make forward progress. Otherwise, you don't make forward progress. Some are a little more aggressive than that, where basically they don't count a participant that hasn't been active for a certain period of time, and they decide that that's an acceptable risk. It's very use case specific, though, and there isn't a perfect solution yet. We definitely do need more work in that area. And in fact, if anyone here is looking for a computer science master's or PhD, I can give you the rundown of what we really need research to figure out exactly how we need to do that. That would be extremely valuable. But to some extent, we're slightly winging it now. I mean, we run simulations and we stay very, very conservative so that we know we're safe, but it would be really nice to know, number one, exactly where is the danger zone, like where is the thing that we have to stay away from, and number two, what happens as we get close to it. So one of the things is we tested in simulation where we took a network that was very healthy and we took a network that was unhealthy, and we gradually moved one to the other to say, what would happen as the network starts to break? And what's interesting is that it doesn't like all of a sudden just blow up and there's double spends and all these problems. What happens is the network becomes unstable and slow. So you get non-agreement, you get extra rounds, and you get this sort of soft failure that we hope would incentivize people to say, hey, there's something wrong, we better fix it. So that's good, but we really do want to know, like, what are the exact theoretical constraints to be sure that the system is reliable? How do we know where we are relative to those constraints? And that's definitely an ongoing research area.
Okay, so that's why you need gateways, right? So that you can reduce number of active participants, so that 80% will not be
Well,
too
and
much.
the other advantage is if you use a system like Ripple, where the system is tracking a virtual asset, if the system blows up, notionally, you can constrain the problem because the gateway still owes you the money. So if you give me $100 and I give you an electronic balance on one of these systems, and the system blows up or fails in some way, I still owe you that money, right? The system was just recording the fact that that obligation existed. But for Bitcoin, you can't do that. For Bitcoin, if you have a Bitcoin, all you have is a number in a computer, and if something happens to that number, you're just out the money. So a lot of people will say that like counterparties are bad because the counterparty can fail, but counterparties have the advantage that if the system fails and the counterparty doesn't, you still get your money.
Yeah.
So it's a trade-off.
So you mentioned how blockchain software needs to be like a fortress, and I'm curious, do you deploy your software with any sanitizers enabled or things like that?
We typically don't run too much of that stuff on live, like production machines. But one of the nice things, you have two sets of data flows. So you have the data flow that's the transactions and the ledgers, and everybody has to follow that to monitor the network. And then you also have like local queries, people who want to know information about what's going on the network. So one of the nice things is you can completely separate those. So the servers that are tracking the sort of canonical, reliable information, you can keep completely private. You don't have to give people access to them. And then the servers that are sort of widely accessible to the world and people can query, they can't harm the network. They can only harm themselves. We use all kinds of sanitizers. We use Valgrind. We use, what is it called, TSAN, the address sanitizer. We use a variety of tools to analyze live data. The other nice thing is it's really only failing on the transactions and the ledger manipulation that's a problem. And we can replay that stuff from historical data. So we can replay everything that happened over the past day on a machine, and we can watch that happening sort of in simulated time rather than real time. So we can test new code on old data. But the problem is still, if someone figures out an attack vector and they launch it live, it won't help that we've figured out the attack or that an address sanitizer has caught it or some sort of piece of code has caught it. If it's already applied to the ledger, and we can't like manually screen each transaction before applying it because of the response time. So that does have some value, and it's definitely good for backtesting, but it's not as useful for protecting live systems. Thank you.
Hi, I was wondering how sensitive your code base is to compiler vendor, optimization flags, versioning, and how you mitigate that?
So we compile our code regularly on GCC, Clang, and Visual Studio. Not too often on ICC. We get pretty good code generation on all of them. Sometimes one will find a bug that another one doesn't, which is also nice. It has not been that sensitive to much. Optimizations do make a huge difference. Any type of memory checking will just put the performance in the toilet, which probably is an indication that our code is still doing more copying than it needs to. But we've gotten really good performance out of all of the major compiler vendors. And I think it's also very advantageous to compile your code on multiple platforms and multiple compilers because compilers sometimes won't report warnings and another one will. Some compilers are tolerant of code that you really shouldn't be doing, whereas another one may not be. Building on a variety of compilers is definitely helpful. But we haven't found it to be particularly sensitive. Okay. Just like compiling in debug mode, particularly with memory debugging, is horrible, but everything else is pretty good.
So lots of good application stuff, lots of good high-level programming stuff, so you must excuse me for asking a fairly low-level question. I had to back off an attempt to ban slicing. Would you encourage me to fight that fight again? Because it's painful.
So yeah, I mean, I think it is the biggest problem with C++ today. Like if I could push my magic button and make one problem go away, it would be slicing. I don't know what the solution is. I would love to see people, yourself, like coming up with some. So standard variant, I think, is going to be one possible tool, and we've used all different tools on different things. But yeah, we need some. We would benefit a lot, I think.
I tried to press that button, but there was a lot of old code out there. My conjecture is that it's essentially all bugs.
I would have a hard time disagreeing with you on that. Yeah, I will agree. To some extent, I'm sounding the alarm. I think it's very surprising behavior for every new C++ programmer, and it rears its ugly head. Sometimes late, for people who are not, decades of C++ experience, sometimes you'll almost finish a piece of code that you spent a long time on, and suddenly discover that slicing means you use the wrong design from the very beginning, and you're like, well, crap! I just spent 3 days working on something, and it's just not going to work because of this C++ issue. And so yeah, I'm not going to, it doesn't ruin the language for me by any stretch of the imagination. It is the very worst thing, though, I think.
But thank you. That's good.
You mentioned that you're salting your hashes with random numbers. Given that it's open source software, do you have to worry about the seed that you use on the random number generator, and how are you getting the entropy or whatever that you need there?
I'm so glad you asked that. So that's actually a fairly well-solved problem, except when every once in a while a failure to do it exactly right rears its ugly head. But we know how to solve that. So the computers that we use in the real world are not Turing machines. They have connections to the real world, and they get randomness from many sources. And the biggest one is on a modern x86 CPU, they have an instruction cycle counter. And the clock that generates that instruction cycle counter beats against the network clock and other clocks in the system, and it causes randomness in the time at which data arrives, and we can mine that randomness. Every Linux distribution does that already. Windows has some proprietary solution that we're told does that. I don't know if we believe it, but it seems to. Systems save randomness on shutdown, and they reload it on startup to have them to start from an unknown condition. And one of the cool things is as long as you have enough randomness at some point, you can produce an essentially unlimited supply of random numbers. So if you give me 128 random bits unknown to an attacker, I can produce a gigabyte of unpredictable data or more, and it's at least computationally unpredictable. Some people say, well, they want true random numbers and they don't want pseudo-random numbers. I kind of think that's like the difference between holy water and water. True random numbers are like holy water. Like some people think that it's a great thing, but there's no test that can prove the difference between the two. So that's kind of, we use pseudo-random numbers, but we mine true randomness from the system to make sure those numbers are unpredictable. Now, there have been some well-known cases where people have gotten that wrong. There was a bunch of Android Bitcoin wallets that had a bug in the Android operating system, I believe, or in one of the libraries they were using, that caused them not to produce random keys, and that was a huge problem. But we know how to do it right. We just have to keep remembering to do it right. One of the cool things that makes that easier, though, is if you take randomness from a number of different sources and you put it into a secure hash function, Your output is secure as the strongest input. So you can take input from dozens of sources, even some that you don't think are particularly strong. Like you could get some from a server, and maybe you don't trust that server, but it doesn't do you any harm because you're as strong as the strongest source. But yes, it's very important to get that right. Very important to get that right. There have been some spectacular failures.
All right, thanks.
One last question, if that's okay. So you mentioned you used Clang, Visual Studio, and GCC, right? And you mentioned that you have some select use cases when you use inline assembly. So my question is, do you have some good advice to make it relatively portable? By relatively portable, I mean I only care about x86 and x86-64. But even though I only care about this, I still have to change the syntax. Say in GCC, I have to specify the constraints on the registers. On Visual Studio 32-bit, I can use inline assembly. On Visual Studio 64-bit, I have to have it in a separate file. So I'm wondering, did you find some good solution to keep it relatively portable in your code base?
Unfortunately, no. I don't know of any magic solution to that. Most of that, we use the same method that OpenSSL uses. There isn't really a good way to do it. Unfortunately, obviously, inline assembly is inherently non-portable. I would love to see, though, some better cooperation between the compiler vendors to standardize that a little bit, particularly in 64-bit Windows code, where it's just completely, I don't know why everybody seems to think they have to do it. I guess the good thing about standards is there's so many to choose from, as they say. But it does make code maintenance difficult. On the bright side, you don't have to change that code often, and it's usually only a small percentage of your code, but it's going to be painful.
Yeah, it would be nice to have. I think, yeah.
You know, there might be some people from Microsoft in this room. I'm thinking there's probably a couple, right? Maybe some of them could take that message back. Thank you so much for coming. I appreciate it.